Hi everyone. Normally the gas laws are taught first, then those are used to come up with the ideal gas equation. But I'm going to give away the ending, and I'm going to tell you about the ideal gas equation first, and then use that to derive the other gas laws. Okay, the ideal gas equation. PIVNERT, PV equals nRT. But before I give you that, this is for an ideal gas. Meaning that it follows the kinetic molecular theory. It follows the KMT. Now, there is no such thing as a theoretically ideal gas, but we could get very close to it, and this equation will apply. There are correction factors for non-ideal gases, but I will not be going over that in this video. We will depend on PIVNERT, PV equals nRT, and let me give you the units for each of these variables. P is pressure, and for this equation to work, it's going to be 1 atm. Oh, not 1. The units are just atm, atmospheres. The volume is going to be in liters. The N is moles, and it's just MOL. T is temperature, and that's going to be, has to be in Kelvin. Okay, so this R is a question mark. But before we get to this R, which is the gas constant, is this relationship, or are the relationships here intuitive? So if I, for instance, if I raise the temperature, what's going to happen to the pressure? The pressure goes up. Whoops. But that assumes that the other variables are constant. So that is V and N constant. Okay, what if temperature goes up? And what's going to happen to the volume? The volume goes up as well. Okay. In this case, P and N are constant. Okay, so we could draw a lot of different relationships comparing two variables using PIVNERT. This is the ideal gas equation. Okay. Now let's get back to R. R is the gas constant. And we saw R before. In this equation, kinetic energy equals 3/2 RT. R was 8.314, and the units were joules per mole dot K. So looking at the units of these variables, we have moles, we have temperature in Kelvin, K, but we don't have joules. This is not the R constant we are going to use for PIVNERT. For PIVNERT, the R is going to be 0.0821, and the units are going to be liters dot atm over mole dot K. If you input this value with the units, the moles will cancel out, the K will cancel out, and you'll be left with liters atmosphere. Well, that's what we have on the left side, atmospheres and liters. Alright, so this is the R constant you are going to be using when you're working with gas. Now, that's it for the ideal gas equation. That is the ending. That is the climax. So, what in real life, the gas laws were first developed, which derived this ideal gas equation. So what were these gas laws? I have trouble memorizing the names, and most professors, though, want you to know the names of these different gas laws. So there's going to be, I'll go over 3 in this video. There's going to be Boyle's law, okay, and that's always taught first, followed by Charles, okay, Charles' law. So Boyle's and Charles are always taught together, and then, not as popular, but I'm going to show you Avogadro's law as well. And they relate, for Boyle's law, well, actually all of them relate volume to some parameter. So Boyle's law is volume and pressure. Charles' law is volume and temperature. And then Avogadro's law, it has to deal with moles, so you can imagine that it's volume and moles. But again, they all relate volume to some variable. Now you got to assume that all the other variables are constant, as well as the R. Okay, so the law is reduced to an equation that's very useful. So let's start with Boyle's law. You start with pivot, PV equals nRT, and if you want to relate volume and pressure, you put all the variables on the left and all the constants on the right. So you notice that for this Boyle's law, okay, you notice already that these are all constants. Why? Because if you're comparing or relating volume and pressure, you're assuming that all the other variables are constant. So at constant amount and at constant temperature, these terms on the right all are constants, and when you multiply, they're constants. But these are the variables. Okay. So we have constants on the right, variables on the left, and that is going to give us Boyle's law. Boyle's law is this: since this is a constant, whatever pressure and volume we have in the system, it's going to equal a constant, and that's going to equal another set of pressure and volumes, and that equals a third set of pressure and volumes. Those were all equal to some constant. So what Boyle says, well, if you have two situations, situation 1, the pressure and the volume of that situation when multiplied will equal the pressure and the volume of a second situation and a third situation. So the problem here is, for instance, if you have a balloon that has a certain volume and pressure, well, if I change the pressure and get a second pressure, how does the volume change? What you notice here is that these are inversely proportional. As P goes up, because they're equal to each other, as P goes up, V goes down. Okay, so that is, and literally the ideal gas equation already sets it up with the variables on the left. P1 V1 equals P2 V2. Now, a hint. I know that for Pivnert, we need pressure in atmospheres, volume in liters to be able to use this R constant. But let's say volume 2 is the one that's unknown. So when you solve for volume 2, you get P1 V1 over P2 equals V2. And the units of pressure would cancel out if they are consistent. What that means is that you don't have to have pressure in atmospheres. You could have them in torr, because ultimately the torr will cancel out and you'll be left with the units for volume. Likewise, the volume doesn't have to be liters. Whatever that volume is for V1, that's the units you're going to use for V2. So in this, for these ratios and these equivalencies, you don't have to convert the pressure. You just have to keep the pressures consistent. Oh, did I say pressure? You don't have to convert to different units. You just have to keep the units consistent. So if your V1 is in the volume, right? Let's say centimeters cubed, your V2 will be in centimeters cubed. Alright? And then keep the pressure units consistent, they will cancel out. Again, this is now boils. Okay, so we'll remember this as boils. What about Charles? Can we do the same trick for Charles' law? Get all the variables on the left, get all the constants on the right. So in this case, we start with PV equals nRT again. So now we're going to do Charles. Charles relates volume to temperature. V is already variable on the left. We're going to divide it by the variable T equals N, R, and then P is going to be constant in this relationship. So we bring P over. Yeah, keep doing that. P. So now this side, N times R over P, that's the constant. So V over T, in any situation, we're going to make it equal to this constant. So V1 over T1 equals a constant. V2 over T2 equals a constant. V3 over T3 equals a constant. And we're going to set those V's over T's equal to each other. Therefore, just like in Boyle's law, we have P1 V1 equals P2 V2. Now we have V1 over T1 equals V2 over T2. Now this is a little bit more strict about the units because we do have to convert temperature into Kelvin if you're given Celsius. That is set in stone. So T has to be Kelvin. Okay. That's the idea, because on the Celsius scale you could have the degree 0, and anything divided by 0 is not valid. Okay. Or you could have Celsius as a negative. Kelvin cannot be negative. All right. So you know that whatever Celsius you have, you're going to add 273.15 to get the temperature in Kelvin. Okay, and this is true for anytime you're looking at gases. Go ahead and convert right away to Kelvin. The volumes can be, again, in any units as long as you keep them consistent. We can never have a negative volume, just like now we can never have a negative temperature with Kelvin. This is Charles. Okay. Can you do the same thing for Avogadro's to get a relationship between volume and moles? Start out with Pivnert and rearrange so you have all the variables on the left and all the constants on the right. V over, now Avogadro wants to relate volume and moles. V over N equals R T over P. Is that right? Okay. Now this is constant. So in situations 1, 2, 3, etc., the volume over the moles will equal the same constant, same number. Hence, Gauger's law would be this. Now, there are other laws. Actually, yeah, there's a couple other laws that I'm not going to go through here. There's Gay-Lussac's, okay, and then there's the combined gas law. Again, we're not going to go over that here. But if you know what you're relating, just start with PV equals nRT and get the variables on the left and the constants on the right, and you should be good, right? I think the combined gas law is relating actually three variables: volume, pressure, and temperature. Don't quote me on that. But these are the three main ones, and these are the ones that you may need to memorize the names: Boyle's, Charles, and Avogadro's. Okay, moving on. Let's talk about what chemists know as standard conditions for gases. So, standard conditions for gases. Okay, this is a little bit different from our standard. If you recently looked at thermochemistry, there are standard conditions for delta H naught, or delta H 0. So that's delta H measured under standard conditions. Well, for thermodynamic parameters, the standard temperature is 25 degrees C. But for gases, you got to remember this. For gases, T equals 0 degrees C equals 273. I'm not going to put 15 K. That is standard conditions for gases. Standard temperature. Standard pressure is 1 atmosphere. So these combined, they call it STP. So at STP, standard temperature and pressure. Okay. All right. So let's go back to PV equals nRT and plug in these numbers. Okay. We have a pressure of 1 atmosphere. Okay, and if you're pretty confident about the units, I typically don't write them in the actual equation or the work that I show. Volume, volume's an unknown, equals, N is an unknown, R, 0.0821, okay, that's the gas constant that we should use for gas laws in the ideal gas equation. Temperature 273. So what am I solving for? Let me solve for V over N, volume per mole. And what is that? How do I do this? I just multiply 0.0821 times 273, 22.4. 22.4. Now, what are the units? What are the units? Well, if this is equal to volume over moles, then your units would be liters per mole. Liters per mole. Let me just double check. Because this one, right? This one is liters.m over mole.k. So the k's cancel out, right? And then when I divide by the pressure, the atmospheres cancel out. So do you see how it's liters per mole? This is a great conversion. So this is a very, maybe not great, but useful conversion. Because what you could say is at STP, 1 mole of gas occupies 22.4 liters, regardless of what the gas is. It could be helium, it could be H2, it could be N2, regardless of what the gas is. Okay, so let us make a purple box. Okay, purple boxes typically for me are the conversions, and we'll just put simply 22.4 liters per mole. But remember, it has to be at STP. At STP. Alright, so if you're given, if you're measuring gas at STP and they say, well, the volume is 11 liters, you can automatically say that there are about 0.5 moles of gas, right? Because you would take 11 liters times, do you see how you have to multiply by the inverse? 1 mole over 22.4 liters. And yes, the liters will cancel out. That's approximately 0.5. Again, please be very, very careful. It has to be at STP. This number doesn't mean it's not true if it's not at standard temperature and pressure. Okay, so that's a discussion about standard conditions. I have one more short topic to talk about in this video. Actually, let me make this static, the focusing. Okay, one more topic, and that is density. If you recall, density can change very quickly with gases. So gases have variable density. That's not true for solids and liquids. Okay. That's because, you know, gases are compressible, or they expand to fill up a volume of the container, and so the volume is variable. Okay, let's start with PV equals nRT. So here's the derivation to get density. PV equals nRT. Remember that density for gases most likely will be measured as grams per liter. Grams per liter. Okay. Well, we don't have mass here in this perimeter, but we do have moles. And you know that moles can be converted into a mass. Moles can be converted into grams. What I want to do is I'm going to rearrange the equation so I have N over V. So that V is now liters, right? It's in the correct position. How do I do this? I brought the V to the right, and I have P over RT. Now, that's not grams, that's moles. But you know that if you multiply the molar mass by moles, you get grams. So that's what I'm going to do. I'm going to multiply, and I'm going to use the fancy symbol for molar mass. Big M, but kind of the curvy one. So again, we're going to multiply by molar mass both sides. So to figure out the density, you do need to know the gas, so you could calculate the molar mass. And we have here times N over V equals and we have to multiply both sides, right? PRT begin. But the thing is, when you have molar mass times moles, you get the mass, right? This is grams per mole times mole. So we get grams on top. So that's perfect, because that will reduce to what? That will reduce to mass over volume equals P, fancy molar mass, RT. You know what this is? That's density. That's grams per liter. This is D. So, your final equation is D equals pressure, molar mass of the gas, over RT. Now what's important is, because we're using these variables that are describing gases, you have to remember that this density is not grams per milliliter, something that you're more used to. This is in grams per liter. Now the thing is, that's how to figure out density, if you know the molar mass. But also, you can solve for molar mass, which is that fancy M, if given density. So obviously it works both ways, right? You could figure out density if given molar mass, or you could figure out molar mass if you're given the density of a gas. Alright, that is all I want to say for this video. We had a lot of equations. They're going to be very useful because you have all of these different relationships, and now at the very end we're even able to get density by rearranging Pivnert and incorporating the molar mass of the gas.